Cool, right. Thanks, everyone. This is macOS Kernel Fuzzing. So I'm James, and Alex is down there. He'll be up shortly. So get cracking. Quick agenda, I guess. So these are the things we're obviously going to cover. So we're going to go through system call fuzzing. We're going to go through our attempts to scale up the fuzzing. We're going to go over our approach to trying to get code coverage for macOS as part of the fuzzing. And then Alex is going to go over IOKit and Mesh fuzzing, comparisons between our two fuzzers, and just some conclusions and any questions at the end. So, OS X fuzz. This kind of came around from our Windows kernel fuzzer, which we released last year at DEF CON. And the idea being is obviously we want to try and avoid privesks, for things like sandbox escapes, getting root, et cetera, et cetera. And we found that the fuzzer that we built last time around was pretty effective. We found a whole bunch of Windows bugs targeted at Windows 7, but it also worked on Windows 10. And it was also pretty scalable as well. The whole point of the fuzzer that we released last year as well was that it could be targeted against other systems. So we wanted to try and see if we could get it to work on macOS as well, as it's obviously quite a popular target nowadays, and with iOS as well, seemed like it might be fun. So just go over some basic principles of the fuzzer. The first thing we have is this a bunch of functions which we can call in the fuzzer that just return fuzz data to us. So these cover all the basic types that you might expect. So your ints, your chars, everything else. We say fuzzed values as part of this, but we don't really mean fuzzed. And the reason behind this is we want the fuzzer to actually be successful in executing system calls, but if you just put in garbage data, it's just not going to work. The OS is going to catch anything that doesn't make sense. So what we do is we tend to return sensible values. There are some edge cases in there, but for the most part, we want the system calls to work. And as I say on the slide, it massively increases our likelihood of the call succeeding, which massively increases the chance of actually finding bugs. The other part to the fuzzer is what we call the object database, and this just allows us to store things that you would use as part of system call arguments as well. So these are things like your file descriptors and things like that. So what we do here is we just create a whole bunch of valid objects at the launch of the fuzzer, and every time a system call or some other call returns a valid object back to us, we stick that back into the object database too. And what we do is we pass these objects around throughout a fuzzing run. And this kind of works quite effectively in finding things like use after free bugs. It's been pretty successful for that. One of the things we've done since we built the fuzzer and presented the fuzzer last year is we can now ask for a specific object type. Obviously, if your system call is expecting a file descriptor, but you give it something completely random and garbage, it's going to crash out. So what we do now is the capability to ask it for a specific type. So there's some examples there of get random object by name for IO surface ref and IO connect T. So this is just some code pulled out of the fuzzer, just showing that we generate all these objects at the launch of the fuzzer. So you can see there, we're just building a load of file descriptors and a whole bunch of IO connect Ts as well. Like I say, we can pass those values around during a fuzzing run. So when you ask for an object from the fuzzer, this is actually what you get returned back to you as an object strut. What this contains is the value. So this is the value you would pass to the system call. The next thing you get is an index. So this is actually an offset into the database. So during a repro run, you can't just give it the value you were using before because that value doesn't exist, right? So instead, because the fuzzer should work in the same way on each run, you can just call into the same place in the database and you should get the same thing back. And the other thing you get back is the tag. As I said before, you want to make sure that what you're getting back from the object database is what you're expecting. So if you're expecting a file descriptor, you'll be able to check to make sure you've actually got a file descriptor back as well. So syscalls. We just pulled the syscalls, BSD syscalls out from the source code, which Apple make freely available. So there's a file in there called syscalls.master. And we also added in main straps as well as a separate table. Initially, we were just incredibly lazy and just wrote a script that pulled out all the syscalls and just grabbed all the arguments, and we tried to turn those into argument types that the fuzzer would understand. So if it was an int, we would go, right, get a fuzzed in. If it was a file descriptor, get a file descriptor from the object database and everything else. And if we didn't know what it was, then we go, well, here's a void star. Try and make sense of that, which kind of worked initially. The other cool thing as well is, so initially we were just using assembly for calling the syscalls, but there's actually just a really nice little syscall function that you can call. So you literally give it the syscall you want to call, the arguments, and it goes away and executes it for you and gives you the return value back from the syscall. So no messing around with assembly or anything like that. It's really nice and easy to use. So initially, this is just how a fuzzing run would look like. So you would go away, you'd pick your syscall, you would generate the arguments for that syscall, and then call it. Really basic, really easy. As I said, worked okay for really basic syscalls. If it was expecting just an int or whatever, yeah, it'd probably work. Vast majority failed because they were expecting things like struts or whatever, which we just didn't account for. So we were giving it void star. Obviously, the Siskel was picking up on that, and it was just dying. And also the maze traps just didn't work at all for this. So basically, we just had to stop being lazy and write actually each syscall individually. You might think that's not a big task, but there's like 500 BSD syscalls or something. So going through those and writing them all individually took a while and was pretty painful. But we got there in the end. So what we do now is each syscall is actually a separate function. It's the exact same principle, but we actually try and make sure that the arguments we're going to provide or potentially provide to the syscall actually makes sense. So this is things like if it's expecting a struct, well, we'll populate that struct as it's expected to be populated, but with our sort of fuzz data. This just ensures that the arguments we're going to provide are roughly correct, which means the syscall is more likely to execute. If the syscall is executing, you're more likely to find bugs. So the next bit is logging. Logging in a kernel fuzzer is a bit painful at the best of times, I think. The way we've approached it, which I'm not convinced is the best way, is essentially we just log valid C, and I'll show you an example in a minute. The reason we did this is we thought, well, it would be really nice if we got a crash and the log file, we could just compile it and then we got the same crash out at the end. Yeah, that just seems nice and easy. And there's also, lots of tools out there for minimizing C files as well. Creating these login statements up front is really painful and it's just taken a lot of time. But if you get them correct, it should just work, which is sort of the benefit to it, I guess. What we do is we send these logs over a network port to fuzzer control. The reason for this is we were initially saving these to disk, but the log files just wouldn't cache. So if we got a crash, we would miss the last 3 or 4 lines of the log file. So that's kind of not really helpful if you want to try and then reproduce that. So instead, we send this over a network port, and then we wait till we get a response back from fuzzer control, and then we know our log has been received, and we know if we get a crash, we should be able to reproduce it. So that's an example log file. The other thing we do is we log the seed value. So all the decisions in the fuzzer just use rand. So the idea being is we can just seed rand with the same seed value, and we should be able to just run it again and get the same output. So if for some reason we don't get a log file, we should always get the seed value out though, and we can just replay the fuzzer. Bit of reverse engineering and debugging, but we should be able to figure out the crash from that. So this is what a function looks like. This is the exit syscall. Probably don't want to fuzz that. You're probably not going to get very far. But what you got here is we generate a variable ID. So as I said, we log in valid C, but we can't obviously then have a whole bunch of variables named the same because you can't compile that. So what we do is generate a random number to append to our variables. So then what we're doing there is we're getting an int, so we're just getting a fuzzed int32. We'll log in the value that got returned to us. What we then do is we log the syscall that we're about to execute. Obviously, we need to log this before we actually execute it because you can't log if you've got a kernel crash after the syscall. And And then the other thing we do is relog the return value as well. And this is actually quite helpful for debugging. So if we have lots and lots of syscalls that appear to be failing, we can quickly just grep through the log files and figure out which ones are crashing and then try and fix them up as well. We also have a whole bunch of what we call library calls, but essentially this is just sort of a catalogue of common API calls. So these are things covering things like IO service, the hypervisor, IOHID library, and IOKit as well. Again, it's the exact same principle where we're using the get fuzzed values and the object database as well. And again, we've had some success from this as well and getting some bugs out. So this is the IO Connect addref. As you can see there, all it's doing is grabbing a object and then calling it, and then we're just returning we're logging the return value as well. So this is what our new fuzz loop looks like. So essentially what we do is we choose either a library call, a syscall, or a maze trap. We generate the arguments for it, and we make the call. And what we do is we have an execution limit, so either we hit our execution limit and we stop, or we've got preferably a crash, and then we can grab the kernel dumps and the log files and stuff. So that's it for OS X Fuzz. Next up is how we went about scaling up the fuzzing, the fuzzer, sorry. So obviously, we want to be able to run this at scale because you're much more likely to get bugs. The other thing we're really keen on is we kind of just want to be able to do this in a click and let it run kind of way. So we want things that are going to capture our bugs, grab our kernel dumps, revert the VM for us and carry on a fuzzing run. What we don't want to do is sit and babysit the fuzzer essentially. So what we have is a whole bunch of Python scripts that basically control everything for this. So in Fusion, we basically make heavy use of VM runs. So VMware exposes a nice API, so we can give it a VM, it'll go away, snapshot it for us, copy the fuzzer binary across, set up all our logger stuff, set up our panic daemons and everything else, and we can just let it run. We don't have to worry about it. The next thing we've been looking at is QEMU. Obviously, you have to run this on Mac hardware. It's part of their licensing agreement, and we obviously do this, if Apple were here. But the reason we did this is we wanted to investigate code coverage support, which is a little bit easier under QEMU. There were a few challenges to this. So we had to mess around with OVMF and Clover for NVRAM support. We also had to use the IONet driver because otherwise we can't use the IO kernel debug interface, which we need if we get a crash. We weren't able to send our kernel dumps out over a network port. And also, the final remaining issue we've got at the moment is memory snapshot support. So in Fusion, we can just revert to a snapshot, which is a lot quicker. Under QEMU, what we have to do is reboot the whole VM if we get a crash or if we hit our execution limit. So this is just a sort of diagram of how that all works. So we have a whole bunch of OS X fuzzes running on top of a bunch of macOS guests, which run on top of a hypervisor. Then on our host, we have our logger and our Python scripts controlling everything with the panic daemon. So what we have is sort of 3 or 4 Macs set up. And what they do is push all the crashes out to CouchDB. The reason for this is we want to be able to have a centralized place for all our crashes, but we can also do some basic deduplication of stuff as well based on that. So if we've another host or whatever seen the same crash, we'll just dump it out. We're not interested. And we also do some really basic exploitability checks as well. So moving on to co-coverage, we've only really recently started looking at how we might utilize this. So at the moment, we're utilizing NCC's Triforce for the co-coverage. It's a pretty cool project. Like I said, we've only got a really basic setup at the moment. And again, we've had a few challenges with this. We've had to backport all the QEMU patches to support latest macOS Sierra on top of the patches we've had to do to get it to work anyway. But what we will do is we'll publish these changes we've made to support macOS to Triforce, whether we push those into the Triforce project or make them available some other way. We'll try and get those out next week. so other people can get involved in this as well. But this is how it sort of works at the moment with our code coverage support. So what we're doing is we're choosing one of those calls, so whether that's our library call or our syscall or mage trap. What we do then is we start our tracing in the kernel, we make our call, we stop the tracing, and then we take our coverage information. At the moment, we're still working out on how to really effectively utilize that code coverage information, but these are some of the things we want to be able to do with it. So we want to be able to take the information and understand, obviously, if it's hit new paths, because that's going to potentially be more interesting to us. So if it does, then we want to keep that call, keep the arguments that hit the new paths and use it for future runs, maybe tweaking the arguments or something. And the other thing that would be really useful for us is if we're hitting, or we're just constantly hitting the same paths or whatever, we might be able to do some more debugging, or figure out ways to just not waste cycles. I'd say it needs a fair bit of work at the moment. Our original design really just didn't take into account code coverage. Our sort of feeling on it was, well, we're getting bugs, why bother? But it feels like it'll be a nice thing to have going forwards. So now I'm going to hand over to Alex, who's going to talk about the in-memory fuzzing part.
Yeah, thanks, James. So basically, James's approach was looking at the BSD side of macOS, but there's different subsystems within macOS, for those of you who aren't that familiar. So there's the IOKit side, which is the device driver stack, and also the mesh microkernel side, essentially. So my idea was to focus on the common vulnerability classes, so things where there's basically lots of bugs being found in the past. So the device driver stack, IOKit, it basically comes up in every Apple security patch release. So it's a common source of issues. So things like IO connect call method, that's where essentially user space can pass data to kernel space, to a device driver, to an IOKit driver, and handle that and call the selector and so on. There's also the IO registry, which is used for persistent properties. So things which the device driver is going to act on. Then there's shared memory mappings, where the user space can request the kernel maps some memory which is shared between the user space and kernel space. And then finally, a time of check and time of use issues. So I basically wanted to write a fuzzer which would find these kind of issues. The approach I took was to combine static binary analysis, so as much information as I can possibly get from the binaries themselves, with also some kind of dynamic side as well. I also wanted to do as much as I could within memory, because every time you touch disk, it slows down your fuzzer. And with fuzzing, if you can get as much execution cycles as possible, and finding bugs is easier. So for this fuzzer, I developed 3 different components. They're basically, they're called Coral Sun, the first one, which is an IOKit mesh library. But essentially, that's used for calling, using Python to call C functions and IOKit functions. Then there's the KXT-lib, which is used for extracting data from the KXTs, from the device drivers, written in IDA-Python. And then finally, the fuzzer itself, called Opal Robots, which is the fuzzing component and sniffing component of the architecture. I'm using code names as well, just because it seems to be the cool thing to do at the moment. I'm not very good at naming projects, so yeah. But there are similar approaches already. There's been a kernel-based, I think Keen Team or Tencent have been doing similar stuff, but they've never released any code. So firstly, the wrapper library, it's called Coral Sun. It's written in Python, which is essentially a way of compiling C within Python. And it basically makes it a quick way of just testing out, prototyping, fuzzing ideas. So common things which you do when you're fuzzing IOKit device drivers, you'd want to open a connection to the IOKit service. You'd like to call methods using IO connect call mapping shared memory. Essentially, the vulnerability classes which I talked about previously, I was just writing wrappers for this and to support it. I guess that's quite small, so one second. Hopefully you can see that. But essentially, this just gives an example of you can write C code inside of the Python and then essentially have that to handle type conversions between Python and C without actually having to write lots of native C with the Python interpreter. And it's quite similar to Swig, if you're familiar with that. But I like Cython for quickly writing this prototype code. And you can see it can do things like native memory management using malloc. So taking this as an example, IO connect call method essentially takes an array of scalar values. So in Python, that would be a Python array. Then I can manually allocate memory for that. Manually allocate memory. And then the type conversion will be handled automatically. So. And with these, I basically did this. I wrote wrappers for the different, sort of common areas of vulnerability classes and common methods. So mapping shared memory, setting IOKit registry properties, and also sending mesh messages. So the mesh side of things, there's a big IPC subsystem from sending messages from a low privilege process to a high privilege process. Across a trust boundary, so you can use that to kind of exploit higher privileged services as well. So that was my utility library kind of underpinning the whole thing, but I needed a way of essentially pulling out as much information as I could to build up the attack surface of IOKit. So I wanted to automate the extraction of the details from the KXTs. Using IDPython, I basically scripted this up to build a JSON representation of the device driver, and then that way you could get a visual representation of the device driver's attack surface, and also it could be consumed by the fuzzer and used by the fuzzer. I batch ran that against all of the KXTs. There's quite a few. There's maybe a couple of hundred of device drivers and things which you can do to extract this kind of the attack surface from that. So that's kind of my pipeline of how things work. Use static binary analysis to extract the attack surface in IDPython, produce some JSON, and then feed that into the fuzzer itself, Opal Robot. So how do we kind of pull these things out? Well, what do we want to extract? Well, we want to extract the I/O services, so the services which you can call. Under each I/O service, there's different user clients, which are essentially C++ classes for the device drivers and things which you can instantiate within the kernel. There's also a number of dispatch tables which are called I/O external method and I/O external method dispatch, which provide you with the arguments for I/O connect call. And also, finally, I'd like to extract things like the shared memory mappings, if the device driver supports it, or the registry properties, like if you can set a string property, then what are those string properties? So the way of doing that, that's kind of the pseudocode algorithm for this. I used two methods. The first way was using IDA X references and kind of code flow tracing to basically determine what function's called. Look for a symbol name, and then from that symbol name, walk the graph and find out what I'm looking for. So for example, for matching I/O services, then if you loop through every function within the code segment, if it contains new user client in the name, then it's instantiating a new user client, a new IOKit user client. And then if you look for the X references from that and look for type constants, then that's probably a user client. So that was a reasonably good heuristic for matching these things within the binary. Then same thing with the IO external method matching as well. You can loop through everything in the const segment every line in the disassembly, look for cross-references for the function names which you're looking for, and then process that table as well. That kind of worked okay, but it would miss certain things. So I wanted to supplement that with another kind of binary matching mechanism as well, which is just essentially dumb pattern matching on the struts. Because the compiler will basically compile these struts and their hard-coded arguments into the const section of the binary, you can just look for, you can loop over every line within the const segment, see if the lines cross-reference to something in the code segment, so it's a function pointer, followed by 4-bit integers, then it's likely that it's an IO external method dispatch struct. That's a pretty good heuristic and actually pulls out most of the IO device driver dispatch tables. There's a few which do their own thing. I don't really know why this is, but and they just kind of require manual reverse engineering. I think you could probably improve this, like if you take into account like C++ inheritance and vtable structure and how the compiler creates does C++, but my way worked and I was kind of in a hurry and to find bugs, so it was good enough. So what does this look like? So here's just an example of IO connect call method arguments being converted to JSON for the Intel accelerator driver. So you can basically see for the IO user client in there, then the different selector numbers, which are the methods which you can call in the kernel, the arguments, the number of arguments it takes, the size of the data, and the number of the output arguments and so on as well. You can also see it pulls out things like the shared memory mapping side of things. Yeah. So that's pretty good, but there's some limitations on what you can actually do with like kind of the static binary side. Like you know the size of the arguments, so you're going to get reasonably, like your fuzzing isn't going to get rejected straight away by checking of the number of arguments. It's going to get into the function at least, but the data which you're passing into the function, that might not be valid. So you might not get very good code coverage because your data gets checked, validated. So really I wanted like a sample of data which would get me deeper within the functions and allow me to get better code coverage. There's also things like issues with like kernel capture. Like if you get a kernel panic and then you dump it out from kernel space, or you do your instrumentation on the kernel side, then I think it makes reproduction and logging actually harder. So I wanted a way which I could capture this from user space as well and know that I could actually definitely trigger the issues. So my idea was to use Frida, which is a pretty awesome hooking framework. I totally recommend you check that out if you've not heard of it. But yeah, essentially do some hooking, create some pickles of like the data which you've captured, and then feed that into the fuzzer. So this was developed using two modules. There was a sniffing module. So the sniffing module would essentially intercept data from user space to kernel space, dump it to disk by hooking the key functions, and then basically pickling it up, storing it, and providing a persistence way of distributing out these pickles to my fuzzer. Then the fuzzing side, which is the actual like mutation part, that would either load the pickled data if there was some data, and then use that as kind of the base for my mutations. Or if I didn't have any data, for example, because I hadn't captured any, then I would use the JSON data, the static binary side, to basically pick that data, mutate it, and test it, and check if it worked. So here's just a quick example of hooking IO connect call method in Frida. It's like I say, it's really easy to use. It allows you to write JavaScript to hook C functions because it injects a JavaScript interpreter in. So this is just attaching to the function name, finding the exported symbol, and then getting access to the arguments and being able to dump out the arguments and so on. I use Frida quite a lot for mobile assessments, so it's quite familiar with the APIs. there are some challenges with this, though, because some of the I/O service handles and mesh ports, they're essentially opaque to the process itself. So if you take a I/O service reference or mesh port from one process and then move it into another process, it won't really be valid because it's not a valid kind of handle. So the way I got around that was just do even more hooking and basically create a lookup table to kind of track the creation of handles and mesh ports and basically map them back to how they were created. And then that way my fuzzer could reproduce the steps and basically reproduce the exact kind of flow of triggering their code. A quick example of this is that, so here's another hook on the I/O service open method, which essentially resolves the class at runtime, looks at the class at runtime so you know what device driver, or what calling processes, what service has been opened. Then when the function returns, then I essentially read out the data from the handle, put it in my map, and then that way I've got a lookup of the handles. So yeah, quite simple. So what does this look like? This basically builds up a bunch of pickles of the attack surface. You can see there's things for the different I/O kit services, Apple Key Store, I/O Bluetooth controller, I/O Surface, etc. And I'm getting a reasonably decent sample size. If you look at, say, the selector numbers and what methods are being captured through the hooking. And just a quick example as well of, that's just a pickle of me storing the data on disk, which has been captured from the hooking as well. So, yeah. So the problem with that is that when you run a process on macOS, that essentially it'll open similar connections to the I/O kit drivers every time. It'll open up a connection to the Intel accelerator, the Windows manager, and so on. There isn't really that much variation of the data which you're capturing, and really you want to capture as much data as you can to get as much of the attack surface for fuzzing. So what I did was I wrote some. I was thinking about this, how could I do this? I could just sit in front of my computer and then hook things and then use it, but that's pretty time-consuming and a bit of a pain because you have to go through all the menus and stuff, and it's just it's not very cool. So instead, I just wrote some UI automation to just click buttons, slide stuff, and just generally just do loads of crazy shit with the UI, and capture, and that allows you to capture as much data as possible. So things like QuickTime, FaceTime, the settings app, they basically generate loads of different traffic. So, but the problem is as well, you need to make sure that you blacklist certain UI calls because you don't really want the VM shutting down, because it's doing loads of crazy actions. It just goes off and then you've got no captures. You're oh, great, yeah. So, the mutation side, you've basically got all of this data. You've got your static binary analysis scripts, your static binary analysis JSON. You've got the pickled data. You want to feed it to your fuzzer now. So basically choosing the pickled data or choosing the JSON data, mutating it, and then finally making the call, as you do with any fuzzer, really. I also implemented support for leak detection as well. So all the data which is coming back from kernel space to user space, it's possible that kernel pointers will be leaked, and then you could use those to find KSLR bypasses or other kind of kernel memory leaks, which would be useful for exploitation. Yeah. The architecture is pretty much the same as James described. However, I was using I was scaling out the JSON and the pickles to my different Open Robot instances, and then that way that was shared between all my different VMs. So I could have some VMs doing sniffing, some data capture, and other VMs doing mutation, and basically increasing my data set and mutation. and then finally feeding all the repros back to my database, and so I could do triage and logging and so on. So what did it find, like, and how do these fuzzers kind of compare at the moment? So OSX fuzz, like, it's found quite a few use after freeze. It's found a number of heap overflows. We kind of expected that because the design choices which were made with OSX fuzz, like the way it was kind of like reusing essentially descriptors and then freeing memory and then using it again, it was kind of, yeah, that was kind of a common vulnerability pattern with the fuzzer. OpenRobot also found like similar issues, but it was finding some interesting stuff with like uninitialized memory, like being used as like a function pointer call or within kernel space. I also found a number of issues with the I/O registry as well, with like writable I/O registry properties. So the issues which have been fixed so far have got CVE numbers on there. There's still a few which are like outstanding or ones I haven't triaged yet. So they should be coming up within the next kind of patch releases and when I get around to actually triaging stuff, because I'm quite slow at doing that. So yeah. Basically the Siskel fuzzer, like, it's good for use after freeze in the core new kernel code, in the open source new code. The I/O kit is still a pretty good source of bugs. Like, Apple have gone to a lot of extent now to introduce entitlements on the I/O kit drivers to basically reduce the attack surface and prevent you from speaking to I/O kit drivers. But if you can either bypass the entitlements or hit things which aren't protected by entitlements, then you could possibly find bugs in those. It's also really important when you're fuzzing as well to focus on like new areas. So things like when new syscalls are added, or when new functionality is added to an OS. So for example, with XNU, like, because it's open source, you can diff it against the previous version. You can see what's been added, and then you can feed that information into developing your fuzzer and adding like new functionality to hit the new areas. So code review definitely helped me from like with the Apple open source stuff, basically helped me focus on some of the new syscalls, for example. Also, just scaling macOS is more challenging than Windows. Like, there's been a lot of talks on scaling up Windows and cloud support and stuff, and you don't really have that with macOS. So what do we want to do in future? Well, basically, we want to scale it up even more. We were thinking about investigating constraint solving or concolic execution or any of the kind of more mathematical ways of fuzzing to kind of explore more code paths and things. But right now it wasn't really necessary because we were finding bugs even just doing it like this. So I also would like to explore iOS integration as well, and porting my fuzzers across to the mobile platform and seeing what of these issues affect iOS. I've also recently written some code which would target the IPC subsystem, because there's quite a lot of services you can hit, higher privileged services which you can get from, so a low privileged service can send messages to a high privileged service across the trust boundary. And then if you exploit those, you can elevate your privileges. And we also need to do more work on the code coverage and feedback side, because right now we've got the code coverage data, but we need to make best usage of this to drive the fuzzer and provide the feedback. So I want to open source as much of this as possible, so I'm going to start off by releasing my Python IO kit code to make it quick to write IO kit fuzzing or IO kit communication type stuff. We're also going to release an updated version of OSX fuzz, which is built on the Windows kernel fuzzer. So those should be available at our GitHub. At github.com/mdurl labs. And also, I'd just like to say thanks to all the people who have done work in this area previously as well. I was kind of new at macOS. I come from a Windows background. I've been doing Windows from a long time. So it's taken a while to get up to speed on macOS and learn about it and learn the internal type side of things. So some of the people like Ian B has done loads of good bug hunting. for Project Zero. Like Mooney Lead has spoke at PackSec about doing kernel fuzzing, but from a slightly different perspective. And then there's been numerous talks previously on IOKit as well, like over the last 6 years or something. And then finally, there was a Python talk as well about OS X, but which there was no code released from. Yeah. That's it really. So are there any questions?